Isn't that like the best sound ever?
Nice.
Birds chirping. Awesome. And there's the worst sound ever. All right, so I want to finish. I didn't think yesterday we were getting to the point, and we might have finished it, but I want to reiterate what we're doing here on this question. Okay, I think it's very important for us to realize the process for getting our solutions once we've actually manipulated the equation down to give ourselves like tangent of theta equals something or sine of theta equals something, how then we go that one extra step. Because that one extra step is everything we've built up to this point. It's everything from chapter 6 and parts of chapter 5, parts of chapter 7, using the unit circle and all those relationships between the angles on the unit circle. So we solved this yesterday. We got tangent theta. Theta being plus or minus root 3, right? So I separate it. I think that's the best thing to do, so that you remind yourself that there are solutions that are going to come from the root 3, and there are also solutions that are going to come from the negative root 3. Okay? I think if you leave them together as just tangent theta equals plus or minus root 3, you lose that kind of identifier that you're going to have multiple solutions from both. All right, so yesterday we talked about how we can maybe use our calculator if we don't remember the unit circle, and especially the tangent. Obviously, I haven't required you to memorize the tangent function values off the unit circle. If I go tangent inverse of the left-hand side, tangent inverse of the right-hand side, if you, on your calculator, type in tangent inverse of root 3, or you know it from the unit circle that is how many degrees? 60 degrees. Okay? And you'll see that enough, I think, in the next couple of weeks, that eventually knowing root 3 for the tangent is 60 will be almost as common knowledge as the sine of 30 is 1/2. Okay? But I don't think we've been exposed to it enough yet to actually memorize that. So tangent of theta equals root 3 at a theta of 60 degrees. If you were to do this so if you're a person using your calculator and you're in radians, which sometimes it will ask you to be in radians, it's going to spit back pi over 3, but your calculator is not going to leave it in regards to pi, right? So it's going to give you back like 1.04 or something like that, okay? There are calculators, and I don't know if I've got a TI-89 on this computer right now. Let me see if I do real quick. Anybody see a folder that says calculators on it? TI, there we go. Is there another folder that says calculators on it? I might have deleted it. TI 84, 84. Okay. Like a TI-89. See if I can search TI-89. Nope. Okay. Which is it's about $200 calculator. It will, if I'm in radians, give me back pi over 3. Okay. TI-89 a lot of times also will give me back actually the equation for all the infinite solutions that this would generate. Okay. So there is technology out there that's a little bit better. When you get to college and let's say you take a math route, okay, whether you're science or maybe you focus solely on mathematics, you will get to courses beyond Calc 2 that they say, okay, now that we are on the same page in the fact that we understand our algebra pretty well, we understand our calculus pretty well, go get a TI-89 because it's going to do a lot of the prerequisite algebra for you so you can do that much more efficiently, much quicker, so we can actually target the Calc 3, the higher discrete mathematics, the abstract algebra mathematics. So you might at some point end up doing that. But your calculators right now, if I type in in radians and give me back a number that I'm not really familiar with. Okay? So my suggestion, even if they ask the question to be written in radians, do everything in degrees first. Get your answers in degrees, and then take the 15 seconds that it takes to convert from degrees to radians. Okay? And do it that way. That's the most convenient, safest way to do these. I think it's the most logical way of visualizing it as well. For this reason, because when I go and visualize this, does anybody remember, if I'm in radians, this is obviously 0 to 8. Does anybody remember what this is as a decimal? Oh, it's 1.57 as a decimal. Okay? This is 3.14, obviously. I think this is about 4.7-ish. You're not going to remember those. Okay? Or maybe if you do, 3 weeks from now, maybe you forget them. Okay? But I don't think anybody's going to forget that that's 90 degrees, that's 180, and that's 270, right? And we need this kind of picture to render the second solution. We just found out that tangent is 60 degrees, or when tangent of theta equals root 3 is add a theta of 60 degrees, that's one of our solutions. We need the other solution. What other quadrant is tangent a positive value? Because that's what root 3 was here. It's positive value. What other quadrant is positive for the tangent? Third quadrant. Okay? So yesterday, I think we reflected here and said, well, that's got to be 60 as well, right? And then we reflected out over the x-axis and said, well, if that was 60 right here, then this was 60. Reflect again. That angle is 60. And that backs up or reconfirms what we know about vertical angles as well. So if you want to use that approach, that's fine. But the second theta that we get here, remember, is from standard position. It's this angle here. All the way back to there. So what would it be if I stopped here? 180. And then I go a little bit further, so it's 240. There's my second solution there for what theta is. Okay? Now, like I said, if you're a person that realizes that what we did there, and this is the benefit, guys, of knowing other math, knowing geometry pretty well, is the fact that we just did a reflection of 60 across the y-axis followed by a reflection of 60 across the x-axis. If you're familiar with geometry, you understand that that is a 100-degree rotation or 180-degree rotation about the origin. Okay? And if I look at vertical angles, no matter where they're located, are always 180-degree rotations of one another across their vertex that they share. Okay? Well, in this case, the vertex that those two vertical angles share is the origin. So if you want to use vertical angles here to see it at 60 instead of the reflections, I think it's more efficient. Okay? That's probably what I'm going to use most of the time when we're doing these questions together, is that vertical relationship. Okay? So I guess we got 240 that way. So now, if people wrote like tangent of theta, that's what I was saying earlier, if people wrote tangent of theta is equal to plus or minus root 3 like that, they go through this process, they get 60 and 240, and then they, a lot of times, will go to the next question. They say they're done. But they didn't address the negative root 3, right? So that's why I think it's important for us to separate them, okay? Because it reminds me that, yeah, you've got something else to do over here, okay? And it's really the same process, but now I'm going to generate a different angle. When I type in tangent inverse of negative root 3, tangent inverse of negative root 3, that's going to be negative 60 degrees. Okay? Is that all right there, everybody? That being said, then, that would be this quadrant here, right? That would be 60 degrees. And because I went clockwise, that's where that negative aspect comes from. When I'm answering my questions, though, we're always going from standard position, moving clockwise. So when they say theta is negative 60, what are we going to really write that as? 300. Okay, we add 360 to get that coterminal angle. Okay, now that's one of our solutions. Okay, our second solution is going to be in that quadrant, right? Tangent is also negative in the second quadrant. So this angle here is 60, right? What's this angle got to be? 60. They're vertical, correct? So when I trace out my standard position angle right there, I'm not getting to 180, right? I'm falling 60 degrees short of 180. So what would be the other angle of theta? 120. Okay? So those are my 4 solutions to this problem. Is that okay with everybody? Okay. Now I want to talk about. I want to go a little bit further detail with this because there's just some weird intricacies that occur with tangent and cotangent. So let me erase these. Let's. So I think it's going to be appropriate for us guys to not only deal with these. Obviously, we answered in degrees. So our theta is 60 degrees, 120 degrees, 240, and 300. But if I was doing it in radians, 60 is pi over 3, 120 is 2 pi over 3, 240 is 4 pi over 3, and 300 is 5 pi over 3. Okay, so now the reason I want to do that is because I'm going to use GeoGebra to just kind of visualize what we just did, what we came up with, and just setting up GeoGebra in degrees. It's kind of a tedious, painful task because you got to mess with the scale and all that kind of stuff a little bit differently than we do when we want to put things in radians. Okay, and so I've changed my axes here, my x-axis. I just identified it in terms of pi over 2s. You don't have to do that. If you want to leave it as x-axis of integers, that's fine, okay? Because when I plot my function, what do we have? Tangent squared of x is minus 3. We're asking ourselves, where does that cross the equation equals 0, right? So where does it cross essentially the x-axis? You can either leave it in integers on your x-axis, but I think it does make more sense to, if you got the capabilities, write your x-axis in terms of your solutions. So all my solutions were thirds, right? So there we see that inside one interval of 0 to 2 pi. So if I do this, 0 is less than x is less than 2 pi, do we end up with 1, 2, 3, 4 solutions? Okay, and that's the 4 that we wrote down. Now, if I was just interested in looking between that blue interval, I could be done and go on to the next problem, right? If they ask me for the infinite number of solutions, I've got some work to do yet, right? How do I go from one solution to the next inside the tangent function? Remember yesterday I said we're going to add something to these things? We always add the period times k. What is the period for the tangent function? Pi. Okay, and we said we're k, so for all of these, k is an element of your integers, right? Over here, if we were in degrees, we'd be adding what? 180k. Okay, so that's great. That if I put, I don't know if we talked about this, if I look at my graph here, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, it's pretty easy there if I put my x-axis in terms of my solutions, that is those values, right? We've got the right solutions for our problem, okay? Now what I want to say is there is some inaccuracy in those solutions, meaning, I don't know if it's inaccuracy, we've got redundant solutions up there. And if I just want the bare minimum amount of solutions, you'd be wrong here. Does that make sense? I told the last class, on a test or whatever, quiz, I'm not going to count you wrong if you have all of those up there, okay, because they do produce every single solution that we need. However, some of those equations produce the same exact solutions, okay, so it's redundant. I had a professor in grad school that he was a total tool, okay, very intelligent guy, but the way, and he was good, he was a good teacher, but the way he graded just really irked me, okay, but it taught me some stuff. Every time we did a problem in that class, we had to have obviously the right math, right? Okay? We had to write our solutions in the most concise manner, meaning that if there were redundant types of solutions, we couldn't have those. Does that make sense? We had to realize that. We had to pay attention to that. And then once we were done with every single problem, we had to justify the math that we did, meaning we had to write a paragraph, sometimes longer, about the proofs, the procedures, and all that kind of stuff, and why we did what we set out to do, okay, and what allowed us to end up doing that, okay? And if you don't have any of that stuff, or you're missing just a component of that stuff, you didn't get any credit for the entire question, okay? You had to have all that information to get credit for the question. It stunk. I hate it. It was I don't know, the worst 16 weeks of my math classes I ever took. Okay, but it's probably one of the classes I learned the most in. Okay, paying attention to detail and that kind of thing. So you don't know that. You don't know where you're going to go. You don't know what classes, what professors are going to be at the universities that you're in that are going to have those requirements of you. So I want to make sure that we're thinking about what we're doing and thinking about what our solutions mean to us. Okay. When we look at these, look at the. I think it's easier to recognize when we deal with the degrees. Think about that first one. If K is 1 in that first solution right here, what does that produce for you? If K is 1 right here. It'd be 240 degrees, wouldn't it? 60 plus 180. What does this produce you if K is 0? 240 degrees. Are those the same solutions produced? Now, it's a different counting tool. It's a different index. We call it K an index as it marches its way from 0 to 1 to 2 to 3 to 4. It just allows my solutions to jump down the curve. But regardless of what K is, if one of those solutions or one of those equations gives me 240, then I don't need the other one that gives me 240 at a different K value. Does that make sense? Okay. So that second, and usually what we do when we start deciding which ones to keep, we keep the ones with the smaller degree or smaller radian. So we're going to wipe this one out. We're going to say that one is unnecessary. It's redundant. It's providing the same solutions. This one here, let's say K is 1 right here. If K was 1 right here, what would that give you? 300. Well, what would K have to be here then to give me the same 300? 0. And 0 is an integer. So I don't need those two. Those first two there are the ones that are going to be useful for us. I'm going to go to GeoGebra real quick. I'm just going to prove this point to you. I'm going to grab that one there and that one there, and they should be generating the same solutions. Okay, so let's go. So all my ordered pairs are going to be like pi. So the first one is pi over 3 plus pi k, comma 0, right? So ask me to create a slider for k. Yeah. Okay. So this is the 4 pi over 3, and actually I want k to be 0. Let's make this go between -10, +10. We'll go by increments of 1. Make it integers. Okay. So you see that I've got, as I move A through here, is it getting me from one point on the curve to another point on the curve? It's getting me from one solution to the next solution, right? Okay. Now, if I go there, I skip some solutions. but those are generated by the other formulas here, okay, other equations. So that was the 4, what do I have, 4 pi, or sorry, pi over 3 plus pi k, okay? I'm going to create another equation that's 4 pi over 3 plus pi k. It gives me that point right there, A and B, okay? If I look at those 2 points, A and B, kind of pay attention to them as we, see if I can trace them. As I move from K to 0, from 0 to 1, does A, look at where B is. When I go to 1, does A take B's spot? When I go from 1 to 2, does A take B's spot? And A keeps taking B's spot as I move to the right, and then B takes A's spot as we move respectively to the left, okay? So are those two formulas producing ultimately the same results? Yeah, they just lag behind by 1 K value, right? Which is fine, it doesn't matter. So that's the logic and why we don't need those two, and we eventually don't need those two, okay? Because they produce points that we have another way of already developing, okay? I think that's an important thing to think about, okay? Is it going to be critical on a test or quiz? No. Is it maybe critical on WebAssign? I want to say no from memory. I think if you type all 4 of them, it gives you credit, but I don't think you need to, okay? So just be kind of on the lookout for that. All right, so let's get into some questions that let's start with, we'll go with example 2. I think example 3 actually algebraically is an example in regards to how we solve that equation. It should come probably before example 2, but the results that we get, the solutions that we get, I think are warranted to come after example 2. So when we work with these trig equations, guys, like we said yesterday, they're going to fall into some categories, okay? One of those categories is that they're going to be quadratic in nature. Not meaning that they are quadratic. They're not going to produce parabolas, okay? But they have that feature of the first term squared, the second term's the first, last term's a constant, right? Or they might have the first term to be to the 4th power, the second term squared, the last term a constant, okay? So we got 3 terms. We got trinomial in which the first and second terms are related exponent-wise in a 2-to-1 relationship, okay? That's what we've got here, okay? Now, I think yesterday we did something that I think is beneficial here. And we did it in the smaller equations, okay, the more kind of 1-step, 2-step equations. But would you guys agree that those are our variable terms? Those are the things that we do not know. Obviously, theta is unknown, and theta is part of the cosine, the argument of the cosine. So that whole thing is what's unknown. So what I think is a benefit, and it's a very underused process in mathematics, is that I'm going to make a substitution. I'm going to let cosine of theta equal u. All right, and the reason I do that, I'm always, if I recognize that the equation is quadratic in nature, I'm always going to take the b values variable part and let that be u. That makes sense? We did this when we did x to the 4th minus like 7x squared plus 3. We went to that middle b term and chose our u to be the variable part of that b term. Okay, so same thing here. The reason we want to do that now, think about so u squared would be cosine squared, right? So can I rewrite this original equation as 2u squared minus 7u plus 3 equals 0? Does that make sense? Do you see now how it's quadratic in nature? And once you develop this, okay, we have, we're going to rely on our algebra skills. Do we use the AC method? Do we use product times sum or product and sum technique? Do we use quadratic formula? Do we use P over Q, rational root theorem? That kind of thing, okay? This one, maybe the first thing you think about is GCF. Okay, is there a GCF that come out of all this stuff? No. So when that's the case, then the next thing usually with this type of trinomial is the AC method, right? So take 2 times 3 gives you 6. Okay. What two numbers multiply together give me 6, but it has to give me negative 7. Negative 6, negative 1, right? So can I rewrite this as 2u squared minus 6u minus 1u plus 3 is equal to 0? And now remember, we talked about this early on. I think, guys, it's a benefit to you when you group these to group the first two, group the last two, but when you group the last two, include the sign of the third term in your parentheses. Okay? Because when it's positive, it's not an issue, but when it's negative, people struggle with that one for some reason. So if you just look and make sure that you include that sign here at that parenthesis, it's going to make things a little bit easier for you. What do we factor out of these two now? 2u. So it leaves you u minus 3. And now this is the reason that putting that 1 there in parentheses, I want to get this to be u minus 3, right? I want this thing to transform into u minus 3. So what would I divide everything by to get that to be u minus 3? Negative 1. And dividing is the same thing as factoring out, right? So that will give me u minus 3 is 0. So now we get 2u minus 1 is equal to 0. We get u minus 3 to be 0, right? Is this going to give me u to be 1/2? And it's going to give me u to be 3, right? And now this is where we call it back substituting. What was u at the onset? Cosine. So now we're going to write cosine theta is 1/2. Cosine theta is 3. And what that does, that substitution, guys, it cleans things up visually for you. Okay? You can do this problem with leaving cosine squared and cosine in there, and you would end up writing you'd go 2 cosine squared theta minus 6 cosine minus 1 cosine plus 3. And doing that, though, people, I think, get lost. They get confused. Okay? Making the u substitution makes things so much easier. Now you ask yourself, okay, unit circle-wise, where is the cosine, which is the x value, right? Where is that 1/2? What angle measurement is 1/2? $60, right? Okay. Unit circle, x value being 1/2. If you didn't know that, hopefully you do. But if you didn't, can I go cosine inverse on my calculator? 1/2. Make sure my calculator's in degrees, because we're not going to know what the radian decimal looks like. So that's 60 degrees. Now, here's the thing. It's 60 degrees right there. That's where we get the 1/2 for the x value, right? Don't I also get 1/2 for the x value for an angle down here like that? Isn't that angle there 60 as well? But what do we always answer in regards to? Standard position, right? So it's going to be 300. So 60 degrees and 300 degrees are our cosine. For 60 and 300 are where cosine of 60, cosine of 300 is equal to 1/2. And that's how you can check that. Just put that 60 in right there, calculator, type it in, get 1/2 back. Put 300 in, get 1/2 back. You know you got the right ones. Okay? This one here, when is the cosine, what is the x value on the unit circle? 3. It's not. Okay? Never is. Okay? So you get no solutions from this. Okay? That's a domain error, right? If you type it in your calculator, it's going to say domain error. Because if you think about what the cosine function looks like, cosine function looks like that, right? That's a height of 1. That's a height of -1, right? This little equation is saying, when does it cross the line that is a height of 3? Never does, right? Okay. So that's kind of what each one of these last statements is doing, obviously that's an equation that is different than what we started with, but each one of these little last statements is saying, okay, take your cosine curve, take the line y equals a half, and see where they cross. Take your cosine curve and the y value of 3, see where they cross. Okay? That's one way of viewing it. Obviously, you got the unit circle approach of viewing it as well. If I wanted to write these as radians, it would be, what, pi over 3 and 5 pi over 3. And if I wanted the infinite solutions, cosine, you add 2 pi k. Okay, so those are your infinite solutions. 60 plus 360k or 300 plus 360k. Those are your infinite solutions in degrees, right? Okay. I think as we go through these questions, guys, we'll find all the solutions in one interval, 0 to 2 pi or 0 pi or whatever, and then also find the infinite solutions. But know on your homework, usually they ask just for one or the other. Okay. Let's see what this original equation looked like. We had 2 cosine squared x minus 7 cosine x plus 3. We have that there, and we're interested in where it crossed the line y equals 0, or the x-axis, right? Right here, hopefully you see it, that's pi over 3. Right here, if that's 4 pi over 3, that'd be 5 pi over 3, this is 6 pi over 3. So 5 pi over 3. Is that where our solutions were? Pi over 3 and 5 pi over 3? Yeah. Okay. And those are then the only 2 spots between 0 and 2 pi that cross the x-axis. So that's why we only got 2 solutions there, right? Okay. Let's do one more. We should have a little bit of time to do this. And we'll hopefully get through all this, but if not, we'll pick up with the last part of this tomorrow. This one is not quadratic form. This one is actually, I think, a step before the types of questions that are quadratic form that we should maybe look at before we do quadratic form. But the way these solutions show up, I wanted to keep this to the end. When you're factoring, the number one thing that you do when you factor, before you go through all of your different techniques, is a GCF, right? A greatest common factor. Okay, each one of these, so when we talk about terms, a term, guys, is something, it's just the objects that are separated by pluses or minuses. Okay, so that's one term, and that's a term, right? Do they have a greatest common factor? Cosine theta. So let's factor that out. I factor out cosine theta. Okay, that blue thing, so factoring is the same thing as dividing, right? So if I take that blue thing and divide by cosine theta, doesn't the cosine theta cancel? You're left with just 5 sine theta. Okay, if I take the green one and divide by cosine theta, what are we left with? Just 4. Okay, now what we have here, this is always something to be on the lookout for. We currently have the zero product property. Zero product property, which says if you take 2 numbers and multiply them together and you get 0, what does that say about one or both those numbers? They are themselves 0. So cosine theta is either 0 or 5 sine of theta plus 4 is 0. Does that make sense? This one's easy to find. Okay, so let's just kind of work. That was already solved for. Let's just go ahead and finish this one. Isn't this going to give me sine of theta is negative 4/5? Okay. Unit circle wise, if I'm looking at the cosine theta one, cosine theta equals 0. When is cosine 0 on the unit circle? Okay. Those 2 radians, or 90 and 270, right? In degrees. Where is sine of theta negative 4/5 on the unit circle? We don't know that, right? And think about all the equations that we're going to come up with and the types of solutions that you could possibly get. We only know about 17, 16 real convenient points off the unit circle, right? How many points are there on the unit circle? Infinite, okay? So the likelihood of getting answers like -4/5 compared to answers like 0 or 1/2 or radical 3/2, it's more likely that these are the types of questions or solutions that you're going to get. So what do we have to do? Grab our calculator, okay? I'm looking for, so sine of theta equals -4/5. So we're looking for sine inverse then of -4/5. And I want to be, right now it's in radians, and I think radians for us right now are a mess to think about. We'll do this question tomorrow in radians, but let's put it in degrees, and we get that. Okay, I think it's a little bit easier, a little bit more visual for us to deal with radians. Oh, sorry, yeah, degrees, sorry. If I were to draw that -53 is going to be that angle right there, correct? That's what theta is right now. Do I ever talk about theta as being negative in my solutions? What do I have to do with that number to get that angle right there? Careful. I could subtract the absolute value of this from 360. But if I subtract this from 360, it's going to add it to 360, right? So I'm going to go 360 plus that number. So theta is 306.869, right? 897.646, however far you want to go. Okay. But isn't theta, or sorry, is it sine -4/5 in 2 quadrants? What other quadrant would it be -4/5 in? Third quadrant, right? Sine is negative in both the third and fourth quadrant. So what would, if this was 53, what's this angle here? 53. So how do I find my other theta then? Say again? Good, 180 plus F. So I'm going to do it this way. I'm going to negate that and then add 180 to it, right? And I get 233.130102354. Those are both degrees. Is that right? Okay. So let's go through real quick. I'm going to write that original equation. It was, what was it, 5 cosine theta sine theta plus 4 cosine theta. Is that what we had? Now the reason I'm using S here is because I want to take S and rewrite it as 90. Do I get 0? Write it as 270. Do I get 0? Write it as 306.86989. Okay. Now I'm getting, obviously, the more decimal places I put in there, the closer that thing will get to being 0, right? The 5 zeros or 4 zeros right there is kind of confirming that that's the case. And then 233.130102354. We're getting that, so we get 11 zeros and then a 4, right? So that's pretty much 0, okay? I did assign 7-4 at the beginning of the day, so that's open, not due tomorrow. It's like due next Wednesday or something like that. So work on that, and we'll come tomorrow and we'll do a couple more of these problems. Thank you, too.